welcome back. We're now looking at the second part of Chapter 17, and we're going to continue our investigation into charges, and then later on in this lesson, we're going to talk about the forces exerted between those charges. We've already shown that opposite charges attract and likes repel, and we're going to talk about that force a little bit later on. But first off, we need to continue to investigate those individual charges themselves. And a big, very important experiment that we're going to talk about is Millikin's oil drop. Okay, and this gets this is extremely important for basically one major reason, in the fact that it proves the charge is quantized. And we'll talk about that in a second. But he won the Nobel Prize for determining what the charge was on a electron, or the smallest naturally occurring charge. And say, we'll talk about that here in a second. But I'm going to draw the picture real quick. What he did was he took two parallel plates and he put charges on those plates. And now these charges, these plates were fixed. And so basically what you have here is positive on the top, negatives on the bottom. And what he would do is he would squirt little tiny oil drops in between those plates. And so you'd have oil drops here and here and here. And some of those oil drops would have a positive charge. And because we know that opposite charges attract and like repel, those would get flown, get shot right down, because they're going to get pushed away from the positives and attract to the negatives, and they're going to go flying down. However, there were other ones that would sit here that would have negative charges, and when they go in. And so there would be a force that would exert them back up, because they would be attracted to the positive plate and then pulled down to the negative. Pushed away from the negative. So if I were to expand this out just a touch, and again, this is a picture I want you to definitely have, is the fact that if this is your oil drop, and I put it in black, I should probably put it in green so you know which one I'm talking about. If this is my oil drop, it would have a force due to that electric charge pushing it up. At the same time, it would have a force due to gravity, put that in orange, pulling it down. And by balancing out the charges on those plates, he could actually get this thing to float. And so in order to get it to float in there, what he would then figure out is like, oh, okay, I would know how much force it would take. And by figuring out the force of gravity, he was able to figure out the charge on each one of those. And what he found out is that these charges, the charge that he found on each one of those drops, was always a whole number multiple of one single elementary charge. Okay, and so when we say quantize, this is really crucial. That all charges are whole number multiples of an elementary charge. And what that also meant is that there was a one smallest naturally occurring charge, called an elementary charge, that couldn't be made any smaller. Okay, to give you an example, and I'll go into this more detail tomorrow, we'll talk about a lot more tomorrow too, but if you think about our money situation, okay, if you reach in your pocket right now, or you look around what's laying around, you'll find money. Hopefully you're lucky to see things. Okay, but if you have a nickel, okay, you have a nickel. If you have a dime, you have a dime. But all of those that you have are always a whole number multiple of 1 penny. The smallest amount of money you could ever have in our monetary system is 1 penny. Everything else you could possibly have is a whole number multiple of that penny. A nickel is worth 5 pennies. A dime is worth 10 pennies. A dollar is worth 100 pennies. So the smallest naturally occurring unit of money is a penny. Everything you have is going to be a whole number multiple of that penny. Same thing happens here. If you scuff your feet across the carpet and you touch the doorknob and get shocked, you are transmitting a whole number multiple of elementary charges. And this elementary charge is the charge on an electron. One electron carries one elementary charge. Technically, it's the negative one. Oops, that didn't turn out well. Let me start that again. Technically, it would be a negative elementary charge. Okay? A proton, likewise, would carry a positive 1 elementary charge. But that's kind of crucial to know. So again, you're going further distance. Millikin showed the charge on the electron drop, so it's quantized. Quantity is the elementary charge equal to charge on that of a proton and electron. One's positive, one negative. This is important. All charges come in whole number multiples of that charge. Okay? Now note, we will use the SI unit of charge. The SI unit of charge is a Coulomb. C-O-U-L-O-M-B, and we'll talk about that in a second. Okay? But the smallest unit of charge is the elementary charge. And we'll discuss why we use a Coulomb rather than the elementary charge for our calculations tomorrow in class. But I just wanted to let you know, we will use Coulomb as our SI unit of charge. All right. This is something you learned back probably a long, long time ago, at least in 8th grade physical science, probably in chemistry. But we divide matter and how it reacts to get electricity into 3 different categories. Conductors allow charges to flow through. And generally, pretty easily. Okay? They have a lot of valence electrons that allow it to flow freely through that material. Insulators do not allow. Definitely not easily. And semiconductors are in between. And probably the best way to put it, semiconductors, is they're insulators up to a point. At which point in time, once it gets to that point, we'll talk about where that is, it's called voltage. Once you get to a certain point, then they become conductors. Okay, and depending on the type of semiconductor, you will have different amounts and stuff like that. But an example for conductors would be like copper. An insulator, we're talking like glass. And the semiconductor, the best known one example is probably silicon. And there are other ones that we'll talk about as well. But just to give you some example. Now, we got to talk briefly about how we charge an object. Now, we've said before, well, if I rub the object A with the object B, I get that transfer of charge. Well, how do I charge a neutral object with a charged object? And it turns out that there's 2 different ways. The first is called conduction. And this very simply is charging by contact. Now, you don't have these 2 pictures, but we'll draw some in class, or you're welcome to copy these down as well. But basically what you're doing is you're going to take your object that's charged and you're going to touch the uncharged object. And in the process, because everything, now this is crucial here, when charging, everything is trying to be in balance. And that's how things become charged, is that the charge is going to try and balance out. We still have law of conservation of charge. The total amount of charge in a process remains constant. What we're going to try and do is we're going to try and balance it out. So if I look up here, I have diagram 1. I have a negatively charged object here, and I'll highlight that. And I have a neutral charge electroscope. And I'll show you what an electroscope is tomorrow in class. Okay? But that negative charge is actually going to come, and it's going to share it. And so what's going to end up happening is it's going to share that negative charge. And so now when I take them apart, now both objects are going to be charged negatively. And they're going to have the same amount of charge. If I look down here, I have this neutral electroscope again, okay, where they have the equal numbers of positive and negative. And this right here is probably an even better example, okay, because I have 7 positives and 7 negatives. So that is electrically neutral. Here, I bring my positive charge rod close to it. That's going to cause those negatives to attract up. Opposites attract, Paul-Abdul rule. Then if I touch it, some of those negatives are going to leave to try and balance out, to make the charge of the rod the same as the charge of the electroscope. And so now when I leave, I am left with a positively charged electroscope. Okay, so again, the key to remember here is that with conduction, the chargee and the charger share the charge, and therefore will have the same charge at the end. One thing I kind of showed here, but didn't really talk about, is charging by polarization. And this is because of Paul-Abdul rule. If I have my positively charged electroscope, or sorry, positively charged rod here, and I have a neutral object, if you look, if you counted the positive negatives on this object right here, they would have the same number of positives and negatives. But because of Paul-Abdul, because of opposites attract, that charge will rearrange. So the negatives are going to go to one side, the positives are going to go to the other. And so what you have is polarization. Polarization is when you take a neutral object and just rearrange those charges so that it's still neutral, but now one side's positive, one side's negative. A great example, this is why if you take a balloon, rub it on your head, it'll stick to a wall. It'll rearrange the charge in the wall so that you have that attractive, so that the positively charged balloon, if you want to go that route, will attract to that neutral wall by just rearranging those charges. That's charging by polarization. Okay? Now, if I want to discharge an object, I want to release those excess charges, I'm going to touch it with my finger, or I'm going to ground it. And what a ground does is just gives those opportunity for those excess charges to escape, okay, to try and neutralize that object. And so when we ground an object, we're going to basically take the excess charges off of that object. Okay? So the reason we call it a ground is because in reality, when we touch it, we're connecting ourselves to the charged object, which then connects it to the earth. The earth itself is a vast storehouse of charge. You can pretty much take an unlimited amount of charge from the earth and it's still going to be neutral, or put a whole bunch of charge into it and it's still going to be neutral. It's kind of like if you spit in the ocean, how much more water's in the ocean? Well, it's basically unchanged. Okay? Or if you take a cup of water out of the ocean, how much is there and how much is lost now? It's basically unchanged from what it was before. And that's why we call it the ground, because the earth allows us to put the excess charges in or take excess charges out, and it's still going to be basically electrically neutral. Now, the last thing we're going to talk about is charging is called induction. And induction is a little weird because it's charging without contact. Remember, with conduction, we took our charged object and touched the other one. And so they share the charge. With induction, we're going to use the ground to help charge our object. And I'm going to walk you through. Again, this diagram is here. We will draw this tomorrow. Okay, so you don't have to copy this down, but I want to walk you through it, and then we'll actually draw the step-by-step tomorrow. But what you have here is you have in the first step, we have polarization. Polarization. Okay, so we brought the positive there. It polarized out. Sorry, excuse me. So when I bring in step 2, I'm going to connect it to the ground. Okay, so now the negatives are here. They want to try and get to there. And so what's going to end up happening, okay, is that in this case, we're going to actually gain, and I didn't look at this picture before I put it on. I don't like it, but we're going to run with it, okay? If we touch it to the ground, it's going to chase these positives off because they want to try and get away from this positive rod right here. It's going to chase those positives off of there, okay? Or you can think about it in reality, what's actually happening is negatives are going to come up and on to it to try and neutralize those positives, to try and make the whole thing neutral. When we get done, we no longer have that excess positives here, okay? The positives have been neutralized. And neutralized. You get the idea. shortcut. I'll fix that tomorrow. Positives have been neutralized. And so now when we remove our positively charged rod, we are left with a negative charge. Notice the positively charged rod right here never touched the object that we were charging. And in the process, we used a positively charged rod to make our sphere negatively charged. So with induction, they get the opposite charge. Okay? With conduction, they share the charge, they're the same. Induction, they get the opposite charge. Now, this is confusing, so tomorrow we will do a step-by-step diagram on how this is, and I will actually show you in real time how to do this. Also, we will do a lab. If you're in here, we will do a lab where you are going to do this yourself as well. Okay? So that's induction. Basically, everything you have to know about electrostatics is summarized here. Okay, so take a look at this. If you know this, you're going to be solid on electrostatics. Now, we said at the beginning of this lecture that we're going to talk about the forces. We know that charges exert forces on each other. Okay, opposites attract, likes repel. Okay, well, we want to be able to figure out what this force is. It turns out this force is responsible for an awful lot of things. This force is responsible for cohesion, which is a fancy word, but it's the attraction between like molecules. If you've ever done a belly smacker going into the water, it was because of cohesion that it hurt. Okay? Adhesion. If you remember back from 7th or 8th grade physical science or even chemistry, when you're reading your graduated cylinder, hang on, let me draw that. If this is your graduated cylinder down here, the water is in it. Boom, like you have water, 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 water. Well, what happens is the water starts to climb up the edge like this, and you get the meniscus thing. And so what ends up happening is it's a climb. That's adhesion. Okay, and it's also responsible for something we've talked about before in friction. The attraction of those molecules are what is the cause of static and kinetic friction. And so these electrostatic forces really play a huge role in our lives. The guy who figured out how big these forces are was a guy by the name of Charles Coulomb. Okay? And what he used was a torsion balance, very similar to Cavendish. And I'm going to draw this really, really quick. But basically what he did was he did on a long cord, he put a pole with two positively charged, all right, just put charged. I'm going to put positives for now. Two charged objects on each end. On either side, he put another positive here, and on the back side here, we'll put another positive, and this would cause a repulsion. And this would cause this thing to twist. And the size of the charges determined how much it would twist. He found out that the force between those two charges was directly proportional to the product of the charges. So if we call this charge 1 and this charge 2, and do the same thing over here, charge 1 and charge 2, the amount of twist, the amount of force was directly proportional to those charges. But it was also going to be proportional to the square of the distance between them. And so we also found, I'll put this in purple, that the force was inversely proportional to the square of the distance. Now, we've seen this somewhere before, not that long ago. In fact, if we put it all together, the electrostatic force, F sub E, is proportional to, let me put the proportion sign in, is proportional to the product of the charges divided by the square of the distance between them. Hopefully you know, hopefully you've seen this before and it goes, wait, hopefully you have an idea. If you're not sure, we're going to talk about it tomorrow. But he was also able to determine the constant. In order to turn this force into newtons, he was able to determine that the force between two charges is equal to K, which is the electrostatic constant, which on the front page of our sales, I'll show that to you. As the product of charges divided by the square of the distance between them. That K, 8.99 times 10 to the 9th. Newton meters squared over Coulomb squared. And this is, again, the front page of your reference set. So this formula that we had up here gives us the size of those charges, size of the forces. And please note that it's only good for the force between two charges. If you have more than 2, you have to run this formula more than, well, however many times, as many charges there are. You have to run that through. So between 1 and 2 and 1 and 3, and then you have to add those forces vectorially. Whether or not it is attractive or repulsive depends on that opposites or likes rule, the Paul-Abdul rule we talked about. So tomorrow, we're going to do a lot of practice with this. We're going to try it with just 2. We're going to try it with 3 and see if we can add them vectorially. Okay? So, but remember, if we're talking about forces, if here's a positive charge and here's a negative charge, let me change colors. And here's a negative charge. That force is directed along the line in between. So we have a force of attraction and a force of attraction that is directed along the line between the two. So we're going to end here. We'll practice with this tomorrow, do a little more examples with it, and discuss it in more detail. But this is going to give you the foundation of those forces that cause friction, adhesion, cohesion. Okay. So everybody have a fantastic day. We'll see you later. Bye.